Hello. Welcome back to the lab. Today we're going to do something a little different. We're going to do a little ASMR quiet EE for everyone because, well, I need to be quiet. So, we went from a plus minus 15 volt rail to a plus minus 8, and now that means our maximum output voltage changed for every stage of the compensator, so we're clipping. Like, we have anti-windup mechanisms in place just because we saturate the output, but now we're saturating at a different place. We've changed the gain of the loop by adding another amplification stage right by the current sense resistor, and well, that might change the transient response. Now, in LT Spice, I tried to tune these so they'd be basically the same, because I thought our old compensator was a great balance of rock-solid stability and aggressive performance. Coming back to the point then, the main thing we need to investigate is transient response, but there's a few different pieces to that, right? So we're just going to be looking at this control loop in general, this PID compensator that we've built out of voltage op amps. How does the transient response change with different step sizes, right? A 1 amp step, 2 amp step, 3 amp step. We did a little cursory investigation into that, and it seemed like we responded faster to bigger steps. But the complement to that is, how does the transient response change with a fixed step size at different bias points? A 1 amp step at 1 amp versus 9 amps, what does that look like? It's positive and negative, still asymmetrical. So that's really what we're going to dive into. I'm really excited to spend the afternoon diving in, collecting a whole bunch of data, and sharing that with you. So, we did some stuff! We did a thing! Oh, yeah, we did. Alright, so my goal, what I wanted to do with you was walk through all the testing and show you everything that we did, but being totally honest, I'm glad that I didn't, because, man, I sat down like, I don't know, 3 hours ago or something stupid, and yeah, we're still not done. Well, we got the results, but we haven't talked through it, so I guess we've got the oscilloscope, one channel, hooked up with our two 1 ohm resistors in parallel. They're a little underrated, but we're just hitting them with bursts of power, not really steady state. We did some tests on each of the 4 channels. We did some tests on individual channels and just generally looking for stability, consistency, and mapping well to the simulation. So just to show you, this is one of our data captures. So basically what we did is we did 10 to 90 response time, and because we've got a 0.5 ohm resistor, the voltage reading is half of the current. So 2 volts is 4 amps. That's basically what we did in our spreadsheet, is we just calculated what our cursor should be set at vertically for that 10 to 90, and then horizontally we just found where those intersected, and you can kind of see the 4 quadrants there boxing in that transition time. Okay, so yeah, that's kind of where we're at. And then what we did is all of our testing today was at 10 volts, and the reason why I did 10 volts is because higher input voltages, I don't actually expect that to be particularly worse for our transient response. If anything, low voltages will be worse because we'll need to push the gate to a higher voltage to achieve the same current, right? We're pushing ourselves around in that RDS on curve for the FET, and the lower the input voltage, the higher the gate voltage we'll need to achieve. Now, maybe that'll kind of balance itself out because we'll be fighting more of the parasitic capacitances and whatnot with the DVDT and the parasitic capacitances inside the FET, but I just thought, you know, this can go up to 30 volts. 30 volts didn't really feel right. I don't know why. We could have. I just thought 10 might be a good middle of the road. Total sidebar, but I've got a feeling that we can push this thing to more than 10 amps. Well, maybe not because of our sense resistors, but we're playing it pretty safe on the SOA curve. I've got a feeling we can probably achieve a reasonably low burden voltage, like 20 amps at low voltages on the input. So I don't know, that might be a good hack. Go in there, replace the current shunts. But that's kind of an aside. So basically what I did is I took serial number 4 of the daughter cards, which happens to be installed in channel 3. All these are at 10 volts in. Basically we just started from 0 amps and jumped up to 1, 2, 3, 4, then we got bored, did 5, 7, 9, 10, and just looked at some of the results. Then we did the falling transients as well to compare the rising and falling edge transients for one of these daughter cards. And you'll notice that there's one called Little Ringing with the note. This is basically what I saw, right? A fair bit of overshoot and we kind of come down and oscillate. And this was only observed at greater than 4 amps on the rising edge transients, which I thought was pretty interesting. Coming back to the table, the next thing we see the max ringing point, and that's where I started to get a little concerned about stability. So I was like, oh boy, so that basically that ringing and overshoot kept getting a little more, up to 9 amps. And this was the worst that I saw. This was a 0 to 9 amp transient. Response time's pretty good. The cursors aren't lined up where it should be. But coming back to the table, the response time was 72 microseconds. And you can kind of see, we're going to plot that in a moment, but you can see there's this curve of response time based on load step. And the strangest thing to me is that a 10 amp load step was the least ringing. It just snapped right up to where it should be. So there's like that intermediate 4 to 9 amp range where it looks like 0 to whatever amps is causing a little bit of ringing and overshoot. I'm not sure if I really care, but what that tells me is it'll be difficult to make this compensator more aggressive without flirting with even more instability. And it makes sense, right? With a larger load step, our error step will be larger. So it makes sense that we might see a little more ringing and overshoot since we're putting a bigger number into our PID. So the integrator will integrate faster. The D term will be a larger player. The P term also. Yeah, so then the one more point I wanted to talk about was the weird falling shape. So as we were doing the falling edge transients, they were super snappy, super good. And then we started to get to below 3 amps. And oh man, I wish we did like a 30 to 90 because this would have looked so much better. Yeah, the 10, we would get down to almost no current, and then we'd like push ourselves down the rest of the way. So it's like the P term and the D term got us down to somewhere really good, and then the I term had to like drag the gate down to where it needed to be to hit 0 eventually. So yeah, that was pretty weird. I mean, this whole thing, the falling edge shape, even with this strange shape, is still way faster than the rising edge, and I think that's because of our diode, our parallel resistor diode combo to turn off faster than we turn on. But yeah, that wasn't expected, especially because it looked awesome at all of the other bias points. So here, just plotted this a little bit for you. Hopefully you can see that all right. The blue curve is more what I would expect. It's kind of consistent. There's like bows where at large current steps and small current steps it takes a little longer to push it around. The large step makes sense it would take longer because we need to move further. And on the small end, we're just feeding a very small input to the compensator, so it makes sense it would take a little bit of time to move around. The strange thing to me is the huge discontinuity in the in the falling edge, and I think I've got an explanation here, right? So we've got a diode and a resistor in the parallel turn-off stage. So in that very small current step, that 1 amp step, it's possible that the step was so small that the diode was never a factor. Like, we didn't have a big enough voltage drop across that output stage on the FET to really engage that additional resistance, so it was slow. And then we've got the 2 points in the middle where it aligns really closely with the rising edge. The falling edge and the rising edge are almost the same. And then larger steps than that, you see super snappy performance, and I think that's because right now you have the diode and that additional stage turning us off really fast. So take that for what it is. A little crazy, but hey, seems to work. I'll allow it. So the next step, or the next set of tests that we did, and believe me, I would show you every step of the way, but it was super repetitive, right? It's just take a snapshot, adjust your cursors. Take a snapshot, adjust your cursors. Take a snapshot, adjust your cursors. But this one got a little weird because there's a lot of noise, as you can see from some of those scope captures. And you see the couple notes where I have no trig. I literally could not capture the falling edge transients for the 6, 8, and 10 amp. The 4, 6, and 8 amp bias 2 amp steps because the noises or the noise coupled into our scope probe from the switching power supply that we're using were bigger than that 2 amp step. So that's unfortunate. So right, there's some output ripple on this switch mode lab supply. That's just how it is. That's unfortunate really. But we need the 10 amp output, so we can't use the linear one that I've got. The linear one I've got only goes up to 6 amps. So this is just kind of what we have. I think what we're seeing is there's some windup in the compensator. So whenever we jump from 0 to something else, I think we're starting with a wound up I term. And then once we're regulating to something, it snaps around pretty quick. So when we go from 0 to 2 amps, it takes a while to move around. When we go from 2 to 4, or 4 to 6, or 6 to 8, or 8 to 10, you can see the response time is not only very consistent, which we would expect because we're moving the same amount, but also much faster than when we go from 0, right? If we've got our compensator wound all the way up or all the way down, and you tell it to move, we need to get back to around that 5 volt point where the thing will actually start to turn on. It's just kind of how it is. And then once we're around that 5 volt point, we only need to move a little bit, so it makes sense that it would be very consistent. So I'm pretty happy with this. I might need to look into the specmanship of most electronic loads, because it's like, if we were to spec the amps per microsecond starting from 0, and I doubt they do that. If we did that starting from 0, and then, yeah, I don't know, maybe it's just they're using a different control mode. And then channel consistency was very important to me. I don't just want this thing to work, I want this thing to work all the time, and 4 samples is not 1,000,000 or 1,000 or 100, but if we saw a huge divergence in performance here, that would not bode very well for the future. So it's important to me to check this out. I'm pretty happy with this. I actually had to scale in. You notice that we don't go all the way to 0 because the lines looked like they were straight on top of each other when I didn't zoom in like this. And once I zoomed in, you can see when we get to higher load steps, that 10 amp step, looks like one of our channels is starting to diverge from the others. But when I look at the majority of this performance, you can see a pretty tight cluster. And not only do we see a pretty tight cluster, we see that with the exception of serial number 2, and now I don't know exactly why serial number 2 is different. Perhaps we've got a cap that's leaky. It's hard to say, right? I need more data points to really see what this is, but what I see when I look at that pretty narrow band that's chasing each other with most of the data points never even really crossing, what I see is component tolerance, right? This looks kind of like what we would expect to see from a Monte Carlo, and that makes sense because allegedly, we've got a lot of random error from the components, right? There's a lot of resistors, a lot of capacitors, and those have tolerance. And we'd expect that the general shape of the waveform should trace together, even if the actual gains are slightly different. And I'm very pleased with this cluster. We never really took this data with the previous iteration. I would love to start getting hundreds or thousands of samples, but ain't nobody got time for that. And I've only got 4 of these daughter cards built up. 4 is better than 1. Just wanted to share this with you. Unsurprisingly, I think this video landed us in a very typical spot. Our compensator isn't the fastest in the world, but it appears to be stable and it's reasonably consistent, the performance, I mean, between the modules. So I think that what we should do is just tweak the values a little bit off camera, maybe leverage that simulation to get this thing a little more aggressive, but still stable. So there's more to come here. There's more to come. If you like this video and you can't wait for more, let me know by hitting that like button, getting subscribed, or leaving a comment down below. Coming up soon, we'll be making sure that the fault tolerance of this system is still intact after our design changes. That's the short circuit, the surge current, and the overvoltage protection. We're going to make sure that all still works. I'm really excited. I'm so excited for that community edition design. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thank you for watching EE for everyone, and thanks for staying till the end. Bye.